Okay, in our next section, 11.7, called Pascal's Triangle, for those of you who don't remember working with it prior, it's going to be an interesting exploration, but you definitely should be able to see some patterns if you didn't notice them in the past. So we want to find different entries that are in the Pascal's Triangle, and we want to use Pascal's Triangle to find combinations and probabilities. So knowing that, let's go and explore. For those of you who have never seen what Pascal's Triangle looks like, here is a version of it. You can see it is a triangle in shape. It is an unending combination. So yes, the shape is a triangle, but it's going to keep going on and on and on and on and on because we could add other terms to this. So now as you start looking, there's a couple things. This top number or row, row 1, then this would be, or sorry, row 0, and then the second row is row 1, row 2, row 3, row 4, and we can see the different numbers in them. So if I ask, what are some characteristics you're observing? And yes, it could continue, but let's just talk about row 0 through 5 right now. What are you noticing? Okay, I've heard someone say each row begins and ends with ones. There's an observation. That's all we're looking for. Somebody else said row 0 has only one thing in it, where row 1 has 2 things in it. Row 2 has 3 things in it. So my hypothesis is that each row has one more term than its row number. So row 1 had one thing, or row 0 had one thing in it. Row 1 had 2 things in it, one more than the row number. The hard part is you got to remember to start counting at 0, row 0. And row 0 is sort of, there has to be a starting point, but where does it come from? The top triangle is all ones. That's what some people would say. Then, some people know one good characteristic about Pascal's triangle, and it looks something like this. Each previous 2 numbers above it, there's this triangular pattern the whole way. So if I said this and this should add to give me this, there's a triangle. Then these 2 add to give me this. These 2 should add to give me this. My triangle went away a little, but these 2 should add to give me this. So it's a little sieve, as some people like to say. So we could now, knowing that, write this next line. We already know that it starts and ends with ones, and then we look. Oh, this next term has to be 1 and 5 is 6. 5 and 10 is 15. 10 and 10 is 20. 10 and 5, and you see that repetition, and that's another characteristic that I think we should mention. There is this symmetry to this. You can find it if it's an even row, even amount of terms in the row, it's cut exactly in half. If it's an odd amount of rows, odd number of items in the row, I can't say odd amount of rows, odd amount of values in that row, there will be 1 in the middle, and then there'll be that symmetry. Same guys on both sides. So I got a 15 and a 15, then I got a 6 and a 6, I got a 1 and a 1. So Pascal's triangle, this was studied by Blaise Pascal, found out all these different characteristics, and it was used for lots of different things. So our job is now going to be to use it also for lots of different things. So let's just clean it up a little here. Take it back, and I think I even have it produced on this next page, but here we go. If we want to find, and this actually comes partly from chapter 10, combinations of n objects taken r at a time, meaning if I have 5 things, but I'm only going to take them in groups of 3. If I have 10 people in the room, but I want to make committees of 4. what's going to happen. So this is a little symbolization that we saw in chapter 10, but since we haven't really worked in chapter 10, let me go over it a little. C stands for the word combination. Okay? And then if we say C, the combination of n objects taken r at a time, those are the same n and r. This is another way to write it. This is a symbol form. NCR is what like people like to say, or students like to say. So I have n objects in combinations taken r at a time. So n over r is another way. And then all three of these, and I was like, why do we need three? One would be good. But all three of these different notations come down to saying n factorial divided by r factorial over n minus r factorial. So be very careful in your work. Now, you've probably seen factorials before, but we will remind you what they really are. So all we need is that number of terms and how many we're going to take at a time, and we can calculate this combination. So I think I do one right here. So let's look. 10 things taken 3 at a time. All right, with that, there are my 10 things. But that 10 things should have an exclamation point behind it, and I'm sure it does. It's just hiding on us. So let's take it. There it is. Okay. So with that, we would say 10 factorial. Now you should know that 10 factorial really is the number. And again, some of you have only hit this a little, maybe some of you not at all. Whoops. That should not be a comma. It should be a dot. It should be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So 10 factorial, exclamation mark, is nothing more than the sequence of that number multiplied right on down to 1. Now 10 factorial I've written out here, but I stopped at 7 factorial. Because I noticed on the bottom, the 3 factorial wasn't going away, but 10 subtract 3 was 7 factorial. And if I got down to 7 times 6 times 5 times 4 times 3, instead of writing all that, it makes sense just to cancel them straight away. So I took the biggest power up top that canceled with that biggest power on the bottom. That left me fairly nice numbers then. That 3 factorial, though, is still there, so think of it as 3 times 2 times 1. And I think that's what I did as my last step here. So I have a bunch of canceling that I can do. So we're left 10 times 9 times 8 divided by 3 times 2 times 1. And I'm starting to cancel. And when I do, 10 times 3 times 4, or 12 times 10, 120, divided by 1. So our final answer is 120. Now today in class, I will be showing you some things with the calculator on these combinations as well. Now, in the book even they went over a little process using this Pascal's Triangle. Whoops. So we should be able to do a little work from this section, as well as I'm going to have a handout just to practice this canceling with combinations. So we're going to take a couple days when we do this. So I think that's all you need for today, using this combination from chapter 10 and the idea of what the Pascal's triangle looks like. Because the second part of 11.7 will actually use some characteristics from the triangle. So